What debugging misses in the story, it's always, or usually it's you who murdered it, right? You just need to figure out how. It does in plot twists, so we never know how. It's really surprising. So it's maybe useful to think how we actually do this, how we fix the program and make it work. I bet most of you have thought about it, and maybe we can construct a simple mathematical model that will explain why sometimes it takes forever and sometimes it's really a short job. So first, I will talk how we can think about finding the error, then how we can think about how long it takes to see the difference in the behavior of the program and how it differs from what we expect. We will talk about search space and cognitive limits that affect it. So there are many types of errors. You would expect that every type of error has different behavior, right? Because maybe it doesn't compile, maybe it doesn't type, maybe it gives the wrong result from the program. It works correctly until the end, and then the result is incorrect. Maybe the actual result is correct, just appears after 2 hours instead of 5 minutes or 5 seconds. Maybe there is a wrong concept that tries to model the reality. Or maybe user experience is frustrating. And finally, maybe specification doesn't match user expectations. That may be also a software error. So basically, we think that error is a difference between what we want and what we got. So all these errors are folded into a single category. But there are differences still. It's the time that takes to fix the error. So we have something like read, eval, print loop, right? Like your interpreter loop. You change something, you run the program, you print the result. Except that we call it feedback cycle. So basically you code a fragment of a program, then you compile it, you get a result of the program when it runs, then you compare the results and use this feedback, this comparison, to fix a fragment of code. So in a way, you often run the code in reverse, right? You get a difference between what you want and what is there, actually, and try to figure out, like differentiate the program, like it would be a calculus lesson, to find what is minimal difference that will fix the issue. And now the most naive model would be, greenhorn student that really knows very little about programming, changes a single character of the code randomly. I know it sounds like Chaos Monkey, and you would swear that it never happens to real programmers. And next time you swear it, try to debug the C++ template, which is basically a string generation, right? Or try to debug any macro program that is untyped. And there are certainly fragments that have this behavior. Yeah, that you need to find this exact character that you change successfully. And of course, the complexity is atrocious. So we have like alphabet to the power of the number of characters possibilities. It's just search space is atrocious. You have to reduce it. You have to split it in halves, in smaller parts, to really find the error where it is. Here we assume you don't really know the line number of the error. But, with sometimes debugging C++ templates of macro programs, the line may be 50, but the real bug is in the line 45. So we still need to look at small fragment of the program and perform this process. So I wouldn't discard this model as always inaccurate, unfortunately. And if you think that it's always inaccurate, come and teach programming to a very beginning student. And you will see that the complexity when the program grows beyond the first loop is scaling also exponentially, right? So that's why we don't do this. Maybe we have a little bit up student, right? Student already distinguishes the token and can just change a token at a time, right? So we assume that student looks at the variable name and immediately knows this is the wrong token, right? If you have long 100 letters variable names, that is not the case. Then you still have the problem that we talked before. But if not, if it's the average size token, then usually you train your brain to handle tokens as single units, right? That's much fewer. So for example, we replace while with for and one parenthesis with the semicolon, right? Then you have the number of token types. In usual program, it's much, much fewer because you have few variable names in each module, each fragment of the program. You also have few keywords, up to about 100. It's rarely used more than that. Usually, mostly 20 keywords are used. And again, to the power of number of tokens. And then we can continue this process. So, for example, with tokens, we can observe that we can have a help, right? So the VS Code or any other editor can immediately highlight those tokens that are wrong. That decreases your time to debug. So instead of waiting for the compiler to compile it, you will immediately see the change of color. That's a clue, right? It points you to the right location. Now, when compiler gives you a line of syntax error, as I said, that's somewhat easier. But again, experience proves that the line may not be the correct line. So depending on how you design language syntax, it may be very easy to attribute the error to this exact line. Or it may be 10 lines before. That's one of the difficulties with C family languages that have highly ambiguous syntax, right? A lot of shift-reduce conflicts, such things. And that is also the case when you design a new language. You may consider how hard it is to write the syntax that will make it unique where the error, syntactic error, happens. So that you decrease the probability that you devolve this previous strategy, which is basically replacing tokens and random in the neighborhood of the error. So if you look at these errors that I talked about so far, you have a big difference between them. It's time from the moment that you change something to the moment that you see the result. So for Lexer errors, editor will show you the change of color. It's under 1 second. For syntax errors, the compiler needs to parse it, and sometimes you need to parse the error message, so it would be possibly under 10 seconds with some routine. Then if you have a processing error and the program runs from 1 minute to 1 hour, that will be the time that you need to actually find the error. But it may be even more. If the output of your program is 1 megabyte, then afterwards you need to parse this 1 megabyte to find the difference from what you expect. So what you may want to do at this stage is to have some kind of a statistic or post-processing of your program, of this 1 megabyte, to make a short report that you can easily, quickly read and fix the program earlier. Because we always are in this cycle, right? So you code, the program is compiled and processes it, and then you compare the difference from what you want. If comparing the difference takes hours, and in some cases it takes weeks to just compare the difference between intended and expected output, that will increase the time to complete the cycle. And sometimes, if you have latent misbehavior of the program, that's very, very difficult to fix, because you may wait 1 month or 1 year, or forget that you wrote the program, and somebody comes to you and tells you, I trusted this program, and my wife had a scan, and unfortunately, it was X-ray scan. The program dosed the X-ray too much, or maybe it was anti-cancer therapy, and the patient didn't survive it. So it's no joke, right? Latent errors that are very difficult to find on the output are problematic. That's why we use, quick check and sometimes even theorem proving to find the difference between expected and actual behavior in advance. Because after 2 years, it's very expensive to fix. Generally, these errors are more and more expensive to fix when this time increases. There is also another problem. According to cognitive research, for short periods, your learning rate, how quickly you learn from errors, is inverse of the square of time that you wait for feedback. So basically, for short periods, like 1 second or few seconds, if it's 1 second, then you learn 4 times faster than if the delay is 2 seconds. So this time actually matters. If you look at the generalization of the statistics for longer periods of time, look at SuperMemo method. It's actually a nice research paper about how learning works. It's still not a linear relation, right? So at all times, we want to decrease latency, decrease time to find the error and compare the intended result from the result that actually occurred. Now there is another thing that we can talk about, which is we fix the function. We have 2 implementations here. Which is easier to debug? Top or bottom one? Maybe you guess. Who is for the top one? Maybe raise hands. Okay, and who is for the bottom one? So I didn't apply students here. I actually have results of the scientific experiments that unequivocally prove that the top function would be easier to debug for one reason. It has no conditionals. And there is very strong correlation between number of conditionals and difficulties to debug. So if you have so-called cyclomatic complexity of the function of 1, which is basically no conditionals, it's much easier to debug than something with cyclomatic complexity of 2, unless there are hidden traits, right? And when you increase number of loops, you increase cyclomatic complexity by 1. Number of ifs, also, you increase it. So the more nested conditionals, the worse it gets. This is because not just that nesting is difficult to understand, right? It's something more complex. The more paths you have in your function, the more difficult it is to track what really happens there. Because you need to consider that all these paths may happen, right? So instead of one function, you have 2 functions with 1 condition, basically. And nice thing is that you can detect it by the statistic. So you can analyze the program and find cyclomatic complexity of the code easily. Let's take a little bit larger scale, right? So we have a library. I wanted to show you a but then I found out that if I show you a module diagram for most of the code I work on, it's usually somewhat tangled, and you would not see much on this projector. So I decided, maybe I'll give you the proxy. This is just type diagram. So dependencies between different types in one program. So the arrows are the type is used in the other type. The module diagram is usually more complex for large systems. And what happens when you search for a bug in a module that has 3 arrows, and it turns out that code looks flawless? You need to look at the 3 of these modules, right? One of them can contain the bug. So the more arrows you have, the more interactions, the more complex it may be. You can help that, right? You can use the standard library that has been tested by many people. It's unlikely to have bugs. And then infrequently, you will look at the standard library functions to fix, right? But that still happens, right? So UTF is an infamous example. But also network handling functions are an infamous example that once a year or 2, or maybe more often, that you find a bug, and sometimes it's security, and then you are very, very nervous, and sometimes it's not security, and then you say, oh, yeah, I just up my skills, add it to my CV, another standard library bug detected, right? But you need to consider all these interactions. So basically, whenever you build a module, it makes sense to make a short module because in case something breaks, it's only in this short module. But it may be also breaking in the interactions with other modules. So you also want to minimize imports and then exports or users of this module. Another example about library functions. So library function of 3 lines has a bug. You laugh, right? And you know that a lot of these CPY and other C standard library functions had similar bugs that have been fixed over the time, right? Now you fix it, and you have 10,000 users. How many of them actually depended on this behavior? Because you have interactions with 10,000 users. So if you use a large standard library, it may make sense to make your own micro library that just wraps and only exports some of the functions that you tested and only allows using them in case when you are certain what happens. Right? So not to rely on undocumented behavior. Like from regex, you can just discard some kind of symbols that behave differently between implementations, right? Or you may forbid some flags that vary in behavior between Linux kernel versions. You may also depend on the completeness of your coverage, right? So basically, the more tests you write, you may also write the tests for the library functions to make sure, if they have a lot of users, just test the behavior to make sure that you already replicated this bug before you get into the application coding. However, if you depend on many different programmers, then it may make sense. So many different programmers depend on you, sorry. Then it may make sense to just be very conservative about interface you provide, make it very simple, very easy to understand. and provide extra checker or extra warning whenever they use behavior that is not really straightforward to explain. Also, a point to regex and similar libraries that sometimes have esoteric behavior that is rarely tested and then is exposed to the user, right? If you have something rarely tested, don't expose it. Please, please. Because then your chance to break on the next version is much, much higher. So the idea would be to actually make this graph for yourself and decrease the interactions. So after a code review with one customer, we have cut about half of the interactions in the code. And everybody agrees that the code is easier to read afterwards. And that is one example. So most of these interactions may be spurious. Then the final thing. What if you could make a very, very simple interface? This is an example of Shake build system interface, right? So you have abstraction. There is a disk on which you can read and write pairs of keys and values. The keys and values would be usually file name, file content, right? It's very, very high level view of the file system. There's nothing else, it's just dictionary. Then you look at the same pairs, keys, and status of the job in the memory. Then you have this small state machine, loaded job, running job, results, or error. You can test that it always transitions between these states, right? And you have task pool. Task pool basically takes the key, produces the value. While it produces the value, starts working, it updates the state, so you can do many tasks in parallel. And then when it computes the final result, it applies it, it computed the value for the key. So there, each key is basically a unique job, right? And what happens if you have such a high abstraction and you use it consistently? So think about, you need to learn all the library functions here, right? So you need to learn all these types if you want to use them. That's not a good library interface, is it correct? So, did you use a library interface where you know 100 types? Anybody raise his hands? Know and understand 100 types? Nobody, okay. Know and understand 50 types? Anybody raise his hand? No. Know and understand 25 types? Maybe they're shy and not certain, no? Do I really understand this library? It's still 25 types, right? Know and understand 10 types. That's still not a recommendation. Know and understand library of 5 types. Okay, many more people. So basically, you need to think about these interactions because you didn't learn it, right? If you really want to know what happens when you debug it, it really helps to know what happens, right? Because that's what you are trying to guess. Who killed it? I mean, I killed it, but I don't know how, right? You need to understand what happens. So you basically use very abstract notions like monads or this description of Shake interface. I assure you that the whole library has much more complex interface, but you know, the abstraction helps you to figure out what happens, right? So that's another level of decreasing number of interactions or complexity of the code. Use mathematics if you can. If not mathematics, just use a powerful abstraction that looks at least somewhat mathematical. Because if you have mathematics, then usually this abstraction is very, very small and has been explained to few people. So you have a good chance that they understand you the same way as you do. I'm not saying certainty, because there are still examples of people that misunderstand, but similar. So you may think these models are a little bit naive, right? So there is a guy who is called McCabe that actually took certain number of code bases and computed their complexity by counting number of operators, pairs, operators, operands that are the same. So basically, fragments of expressions that are the same. Names of operators that are the same. And he inferred that if you count it, then you have some measure of complexity. And then the time that people spend on a project of a given size to debug it is not linear, of course. It's exponential. With all these techniques that I talked about, so they use modules, they use types, everything, it's still exponential. It's just smaller base, right? And depending on the programming language and other factors, you have factor or the exponent of 1.5 to 1.7 still there, right? So just number of common sub-expressions, and you can decrease it, right? You can, if you have an abstract interface like a monad, you can define multiple monads, and you decrease number of function names that you define, right? Because you know that then you decrease this measure that has been empirically proven to coincide with the time you will spend on debugging it. So there is this general rule. We want to decrease complexity, decrease number of interactions to make the system tractable. And it's not tractable in the sense of, how easy it is to read A and B. It is tractable or intractable in mathematical sense. So we want to decrease this exponent of how much possibilities there are in the state space to fix, right? And high level of abstraction or common interface or less interactions will give us decreased complexity. So ultimate ways of reducing complexity, to summarize this talk, is like, we want to decrease the problem size. We want to decrease the size of the function. And there is also research of how longer functions are more difficult to debug and more likely to contain errors. And there are recommendations of maximum length of the functions in different languages. The same for modules. The same for type classes, for types. It all has optimal size, beyond which it becomes intractable because you need to check too many things, right? Number of conditionals. And these are statistics that you can compute. Or you can just look at the code and decrease them. Decrease latency to comparison, right? So whenever you change something, don't laugh at the people that set up the editor to automatically compile it background and highlight everything beautifully, because this is saving time, right? This is saving a lot of time. The quicker you get the answer, the quicker you make a change. And that especially matters when you have like program that I had this problem during my PhD that always runs the full test suite for about a day, right? That's a very long time, but it was very large test suite with a lot of regression tests. So what I could do, I couldn't decrease time. Then you can increase throughput. You can handle errors in such a way that you will see multiple errors, multiple differences on each run. Then you have thousands or hundreds of errors at each run, because otherwise your work will be too slow. You can, for example, do as I did, which is basically that you automatically see certain kinds of issues and automatically generate unit tests for all exceptions raised or all differences from the expected behavior that were automatically found after a single large run of the program. And then these unit tests hopefully will be much shorter, and they will run in a few seconds, right? So we can fix the issues individually. And reduce interaction, because the more interactions you have, you basically have this intractable problem of too many dependencies there. And it applies to function arguments. So there is also cognitive research that says that we can remember between 3 to 9 items in our operational memory. So it's probably a very bad idea to have more than 9 function arguments. Probably make them into data types, into records or something like this, like flags, yeah? Flags record and just package it together. Because each interaction will make it more complex to figure out which argument is passed wrong. And then reuse abstraction. Because it's basically well-tested interface. It's not even an implementation. It's not well-tested function, yeah? Like standard library function that gives you high reliability and low chance that you use it wrong and it gives you a wrong result. Interface is even better than that, because that's something you understand how it works before you actually need to delve into its code, right? So very good interfaces like monads or applicatives or basically design patterns in object-oriented programming, you know how they work already. You just keep the same interface. And the ultimate abstraction in this regard is often seen in mathematics, because mathematicians usually work on complex problems and need to make them very simple before they are ever tractable. But increasingly you can see it in programming, right? And of course, if you code in Haskell, use complexity, which is tools that automatically finds a lot of these statistics and shows you the hotspots in your code. Some other languages, I would say most nowadays, have some of these statistics, like cyclomatic complexity, size of types, size of modules, number of lines of codes per function, number of functions per module, number of functions per type class, number of functions and implementations per class, such things. All there have their optimal number, so why not to compute this optimal number and compare with what you actually see? So next time you see the type with 200 constructors, you can see there is probably very good reason to do this, and it's probably hard to debug. So as long as you don't actually use it, it's okay. If you want to write the code that you don't use it, right? So, any questions?
Okay, so okay, let's give a warm round of applause. Thank you, Michał, for the presentation. And now, yeah, let's move to Q&A. I saw a question over there.
So you mentioned a point of complexity is nested if statements and how they can make things a lot more difficult to debug. What do you recommend to suggest? Because I agree, but it's easier said than done, because if an employer asks me to add a bunch of complicated business logic, I have to do it, and they won't care about my opinions on functional purity. So what do you recommend to kind of minimize the grossness of the nested functions?
That's a very good point. So when you have a business logic that is described in a way that basically is something like cyclomatic complexity of 10 or even 100, it happens, yeah? We can all tell that it never happened in our project, but it does happen in business. Then the only chance is to break it down like you break down the functions, right? So you need to ask and discuss with analysts to break it down into small pieces. So basically, into pieces that you can describe as simpler than they are. And then when you are programming, you also need to decrease it. So the worst case of cyclomatic complexity is not actually in the code in Haskell or in any other language, it's in configuration of Linux. Nobody really knows which of the flags that are enabled in Linux will give you a working kernel. I'm not joking, it's just impossible, right? There are too many possibilities. So you know that if you have too many flags, it will become intractable. You can try to split it into different modules, right? So this also happens. I'm working in the software house, MegaMakeCode.com, that I founded. And what we sometimes have in such situations, we talk to the guy who goes into the places that have most complex specifications, like Polish Ministry of Finance, right? And he splits it in small parts. The only thing that we don't accept in this case is, no, it cannot be simplified. It has to be, right? Because above certain complexity level, as you've seen from mathematics of it, it will become intractable.
Questions? Okay.
Okay, now we cut it down. Yeah, we have separated the logics that we could, but now we have too much dependency on modules, so.
That's very good point. So, if you are a chemist, right, you see there are chemical compounds that have a lot of different relations, right? They are not very hard. Like protein, there is a chain of basically amino acids, and they interact in many different places, so you have actually complex network of interactions within each protein. And each protein, most of the proteins, when they go above certain temperature, they just unfold and never hold. So the same happens with your program, right? If you have too many interactions, you know it will basically unfold and unroll. What you can do is, when you have too many interactions, you split the modules in this case. Again. And then you try to basically perform a maximum cut algorithm, right? So you find the lowest number of edges in the graph that you can use to split the sets of modules into supermodules. So you basically make a hierarchy. So that basically this network will have fewer connections altogether. I'm not sure if it's clear. Maybe next time I will make a chart, but generally the idea is to make it kind of planar graph as much as possible, and sometimes you also make supermodules to contain these interactions. Yeah, so basically you have a hierarchy of these modules. Yeah.
Hi. I have a question related to complexity. So do you have any recommendation on identifying what are the complexity that are accidental due to maybe language itself or some architecture decision, or the complexity that is essential to the problem you are trying to solve?
This is a very hard question, but we talk about models here, right? So we can pose certain things that have not been yet proven by statistical research. What statistical research tells us, and also research in logic, is that, for example, untyped languages, if you enumerate untyped language programs, there are many more than typed languages, which means search space is much larger. If you use type systems, then the search space of the valid programs is much, much smaller. So generally, if you can decrease this search space that you need to examine to fix the error, that usually helps. That's kind of rule of thumb. And that can be applied to language design. So when you have a grammar that is highly ambiguous, that's larger search space when parsing, and also larger search space when understanding the code. Does it help?
Okay, I'm sorry, but I think we're running out of time. So if you have some code that you would like Michał to debug, you can catch him at lunch. But right now, I would like to invite all of you for lunch. We have 1 hour, and I would like to remind you that we have 3 separate buffet sections. Each of them have the same food. So let's spread it around and enjoy your lunch. When you're leaving, please remember to rate the talk. It really is important for us. Thank you, and see you in 1 hour.